you know that in the next quarter we have this enriched finite element class, and this is basically what really I'm interested about. So this standard FEM and p-FEM stuff that we have seen in this class, it's for me important because it's a prerequisite to really get into the hardcore stuff. Yeah. So we have seen just stuff that you would use in the industry, and it's okay. I mean, they have challenging problems, but this is hardcore stuff. This is the stuff that you can actually do research on. Okay. So let me show you a bit of the types of problems that I am interested in, and these are the type of problems that can be addressed by enriched finite element formulations. Okay. So when are these superior than a standard FEM? Because of course every tool is perfect for its job, right? You're not going to try to hammer something with a screwdriver, right? So if a standard FEM or p-FEM can do the job and they can do a nice job, then there is no reason to go for something more complex. Yeah. So it was Einstein who said, I think, problem has to be
make everything
simple as possible, but not simpler, right? That's it. That's the idea. Well, he didn't actually say it that way.
He said it probably in German.
No. I have the actual phrase. He didn't say it that way, but people then understood it to say that. So problems that require some complex meshing are some that can be addressed very nicely, very elegantly with enriched finite element methods, and I'll show you a few. These are remeshing is also an issue. So you come up with a mesh, and then the mesh is no longer useful after your first iteration. You need to do something about it. So you have like crack propagation, coalescence of cracks, branching, merging, optimization problems where your boundaries are not known a priori is also a type of nice problems that you can tackle elegantly with this type of formulations. Moving boundaries, immerse boundaries. Who has an idea what immerse boundary is? No one. Okay, imagine you want to model this marker. And now I don't want to create a mesh that actually follows that boundary of a marker, but I just include this marker inside a box. That's my finite element mesh. It's just a very simple structured box of finite elements. I'm immersing my marker geometry in that. You can actually obtain a solution, and we're actually doing super nice job in that direction too. Problems with singularities, that's another problem. If you remember in class, we saw that those problems with singularities in category B, right? You can at most get what type of convergence with p-FEM?
Linear?
Well, no. It depends on your elements, but what type of convergence? Algebraic convergence. Well, it turns out that you can actually add whatever singular functions to your approximation to even improve the error and get optimal convergence. So you can obtain exponential convergence back by using enriched methods. Problems with localized or sharp solution gradients is also. So if we add to the formulation a function that has a sharp gradient, then we're basically asking Galerkin, well, try to use this function to reduce the error. So if the function is useful, it's going to assign a generalized degree of freedom to that function. If not, it's going to assign what? 0. So all these are all problems where really can take advantage of this enriched FEM. Problems that require a statistically significant result. So say you have to analyze some microstructure and you have to come up with 100 different packs. Like you have particles inside and you have to arrange them and you have to create 100 different meshes. You really don't want to do that. So you can just use a standard mesh, like very simple meshes structured, and then let the enriched formulation take care of all those different geometries. So all of these are nice problems. So this is, for example, some mesh-independent analysis of microvascular networks, microvascular cooling networks. This is part of my PhD work. So you can see here that on the left you have a standard FEM, and then if you want to create a matching mesh for that, it's a nightmare. But then you can just analyze with the mesh on the right where your channels are independent of the mesh and get the same result. The same result, right? Which is very cool. Of course, it's not easy to do that, but once you get it and everything is working, you get the same. So it's remarkable. All of these problems, complex geometries, all those geometries that you see there are basically independent of the background mesh that was used for the analysis. So you have woven composites, you have this fracture mechanics problem, you have one microchannel at the bottom, fibers, all of that is independent of a mesh, which is very simple. So for analyzing these continuities, these methods are really, really nice. And in our group, we're developing this continuity enriched finite element method. So this is basically what my research is all about. Yeah?
In the previous slide, can you explain a little bit more how is it possible that you get the same results with it looks like very simple mesh?
Because you are adding, yeah, it looks very simple. And you're adding functions. You're adding something called enrichment functions. And those functions basically incorporate into the space some knowledge about the solution that you know, right? In this case, for this particular case, I was very interested in obtaining the temperature field. So I was coming up with some cooling microvascular network. And what I know about that solution is that along those lines that are very slender, so you could actually collapse these two lines, then the temperature field had a kink. So if you think about that as some knowledge that you have about your solution, and you say, well, what if I incorporate a function, an enrichment function that has a kink built in? So that is the way we do it. So you use some a priori knowledge about the solution of your problem to construct enrichment functions that somehow are improving the solution that you get. Yeah? Let me show you very quickly some other problems. This is a work of Angelo Simone. You can see a very simple, like in this particular case, you see all those grains, right? This is a polycrystalline microstructure, and then you can actually propagate cracks through the grains and through the elements with this type of formulation. So this mesh that you have here actually matches the grains, but you don't have to actually even do that. And in my group right now, we're doing that. We're trying to come up with microstructures that you don't mesh the grains nor the cracks, and everything is taken care of by the formulation itself. So it's very nice stuff. Fibers, imagine doing something like that and model that with standard FEM. This is also work of Angelo, so he shows that you can get very nice results by just enriching the finite element formulation. This is my work as a postdoc. I was interested in looking at the response of a heterogeneous adhesive. So this is the problem of statistically representative results. So this is one pack of particles. So in this case, my particles remain linear, and I wanted to see how the material was going to fail. And well, you obtain different types of results. So this is damage response of the material, and you see that here you get all those curves with the same finite element mesh as a background. So actually, all those spheres that you see there are the result of interacting a very simple mesh, structure mesh with our geometric engine, right? It's able to follow and capture the geometry. And this is a simulation where I basically show how this material is degrading as you basically put a shear force first, and then you try to deform this in mode 1, and then you see where the damage is happening. So it's a damage response of a material. Then cracks. Enriched formulations are great for cracks. So if you want to model cracks with standard FEM, you have to come up with meshes that look like this, which are a pain to make. Right? These are not only the mesh is a problem to make. Also, you have to use this idea of quarter point elements, where you are basically the elements that are surrounding the crack front. You have to move the nodes. So these are quadratic elements. You have to move them closer to the crack so that you are able to represent this singularity, right? This 1 over the square root of r singularity of the stress. And so creating meshes like this is really hard. And so for Enriched FEM, you don't have to do that at all. What you see here is perhaps the most advanced crack propagation simulation in the world. This is the work of Armando Duarte, and this is due to hydraulic fracturing. And you see all these cracks evolving in 3 dimensions, and he can actually merge them, and it's very interesting. And everything is mesh independent, right? So all the cracks are going through the elements. You don't have to care about the mesh, the background mesh at all. So here just a coalescence of cracks, also the work of Armando, and he shows how he can do that. Sharp gradients is another problem, as I said in the beginning. So if you want to, let's say you have a localized heat source, you know that you're going to have a very steep gradient, temperature gradient, close to the application of that load. And if you want to capture that with standard FEM, you will have to mesh it this way. Well, not anymore, right? Because if you have a function that is building that behavior into the formulation, and say the function has a sharp gradient, well, you can just do this, right, and simulate that with a background mesh that is very straightforward, very simple. But the function is adding that functionality to the solution. Yeah, and this is my work on immerse boundaries. This is just to show you how really mesh independent is. So here it's just a beam, and I immerse the beam in a mesh, and I just want to take the first vibration mode of the beam. And every frame in this simulation, we just rotated the mesh a little bit, just to show you it's truly mesh-independent solution, right? But it's just the first vibration mode of a beam. Also, my work, this is very current. Actually, I have a PhD candidate working on this. This is contact mechanics, so we can actually use the enriched formulation to model contact. This is an extremely challenging problem to solve. Contact mechanics, because of the nonlinearity, it is super hard. So we're trying to come up with something that is simpler than what is being the state of the art right now. It's very new work. Also, topology optimization. This is also my stuff at work. So my discontinuity enriched finite element method coupled to an optimizer to do topology optimization. But the cool thing here, who knows about topology optimization? Who took Matthias' class? Raise your hand. Yeah. So the difference between these and the standard topology optimization is that this is not density based. Right? So I can cut through elements in any direction. So that is super nice. So basically what we're going to cover in that class in quarter 4 is what is the extended or the generalized finite element method. They are the same method. It's just that it is understood today that XFEM is GFEM applied to discontinuities, but GFEM is actually a network that is more powerful than just the analysis of discontinuities. As I just showed you, you can model problems with sharp gradients or all the other things that we showed. And we're going to look at 2 other types of enriched finite element methods, which are the result of my work and my co-workers, the interface enriched generalized finite element method, and the new one, which is the discontinuity enriched FEM, which is the one that I'm trying to develop very hard for fracture mechanics. And of course, we're going to look at the computer implementation details and so on. So the idea is that we develop on what was given in this course on HFEM and p-FEM, and to really tackle more complex problems. And this is again part of the book. So we have already another 2 or 3 chapters that are related to all this enriched finite element technology, right? And we plan to publish this sooner or later. Any questions about the course?
About this one?
Yeah.
Is it going to be a similar project like this for the assessment?
So what I have in mind is to provide a 1D example again, so that you see how this formulation performs in 1D. 1D, everything is simpler in 1D, and if it works in 1D, it should work in 2D, right? And then a second problem where you're actually modeling discontinuity in 2 dimensions. That is my goal. A problem where you have your finite element mesh that is completely independent of your geometry. That being said, because this is a topic of research, and you have an interesting problem that you want to talk to me about, right? And you want to do that with your own, implementation of Enriched FEM, that's something I would be interested in, because there are lots of interesting things to do in this field. Like all the formulation that I just showed you, I have shown you a few things, but of course these can also be applied to fluid dynamics, fluid structure interaction. So there are some nice directions for development over there too. So if you are really into numerical modeling and you are still thinking about a project and you want to go in that direction, please talk to me, because I have a few interesting development ideas. Okay? Yeah? Well, thank you very much.